Welcome to Maths with Bob. Today we're looking at further applications of calculus to the physical world, and this is the growth and decay 3. And this one is actually, well, very similar to growth and decay 2, but you'll see here, basically this one, we now are looking at, okay, the rate of change of something, okay, is proportional to actually some constant, now minus the quantity present. Okay, so the difference is reversed. You might remember in growth and decay 2, it was this one. It was dq dt was actually proportional to q minus r. That was like Newton's law of cooling and those sorts of things which actually cool down. So we're going to now have a quick look at how we solve this one first of all, and then some applications. Okay, so how do we solve this? Well, okay, the first step, okay, we all know is, hopefully, now is to replace this proportionality symbol with a constant of proportionality, I guess you could say. Now this one here is a constant, okay. So we're going to now try and solve this, okay. So what do? Well, we take the reciprocals again and integrate, but we're going to go through that now, okay. Okay, I've just rewritten the equation here. So how do we actually solve this? Well, first of all, we take reciprocals of both sides. dt dq equals, okay, 1 over k r, the constant, minus the quantity present at a particular time. And you can see here we'd have to integrate with respect to q. So we need to go like this. Integral of dt dq with respect to q is equal to 1 on k r minus q, you can see here, dq with respect to q again. So we need to basically try and do these integrals. Okay, we can simplify this one here to just the integral of dt, which is it's going to give us the t. We can take a 1 on k out here. We're going to get the integral of what? 1 on r minus q. And if you like, you can just write dq here. Now, this is where the difference comes in now, and you know the derivative of r minus q with respect to q is actually minus 1. So what we do is we need to put in what we want, a minus, so it adjusts it to the log, and then we need to adjust the front here to minus 1, and now we can start to integrate now. Okay, so what happens now? Okay, therefore, okay, t is going to equal minus 1 on k ln of r minus q plus some constant of integration c. Okay, again we do the same thing, multiply by kt equals minus ln r minus q plus kc. I put the kc on the other side now and just get t minus kc is equal to minus ln r minus q. And just to help simplify things, put the minus sign on the other side, so it'll swap the signs around, so it'll be kc minus kt now is equal to the positive of ln of r minus q. Then we raise everything to the power e, so we now have, therefore, e to the kc minus kt is equal to, you can see here, e to the ln r minus q, and these are inverse functions, so this just drops out at r minus q. Okay, we have got the negative q there, but this is going to be equal to, as you can see here, e to the minus kc minus kt. Okay, actually it's positive kc, you can see there, positive kc minus kt. Okay, so first up, we normally let t equal 0. Okay, so let's let t equals 0, and therefore we have what e to the kc, the constant, is actually r minus q, and I'm just going to let this equal to a, some other constant a, and then we can rewrite the solution as well, we'll actually rewrite that I'll just rub out a few things. So let's actually go back and try and work out what this is going to give us. Okay, so let's actually just have a look. What will this give us? Okay, so what have we got? Let's just change the color now. Okay, so we have that, if you like, e to the kc, which we are letting equal a, times e to the minus kt is equal to, you can see here, r minus q. And the r is a constant. Okay. And we let this one here be a, so we have a e to the minus kt is equal to r minus q. And then we sort of put the q on the other side, and therefore q is equal to, rearranging this, r minus a e to the minus kt. And this is, if you have a look at this situation, what's happening here is we have basically this r, as t goes to infinity, q is going to approach, so let's actually have, let's have t over here somewhere, t, and we can see that we are coming up from some value here initially, and then we're going to approach, this value r. Sometimes r is sometimes called the steady state. I noticed some differential calculus textbooks actually call this the steady state. And the other part of it is the transitional state, and you can see here the transitional state basically approaches zero, and we eventually approach what's called the steady state. Now, this can be applied to what's called Wilhelm's law. That's with basically reactions and chemical reactions, and then you can also do it with brine and all sorts of chocolate mixing syrup type situations where you look at the concentrations of things changing over time. So we're going to look at an example now. Salty water. We're going to have about, say, 200 litres in. Okay, let's actually just put, say, 200 litres in here. 200 litres, and let's just say there's originally, say, 50 grams of salt originally in our big vat. Now, what usually happens with the brine situations is that we have an inflow rate, okay, coming in, and an outflow rate coming out. So we have an outflow out. Okay. Now, usually the rates are the same, so the level stays the same. But if they're not, they actually turn into a non-exponential sort of situation. But we're not going to look at that case at the moment. So we're going to assume the inflow equals the outflow, if you like. And we're going to put something in at 10 litres a minute. Okay, so the inflow is going to be 10 litres. I'm just going to write it per minute. Okay, and the outflow obviously will be again 10 litres per minute. I'm just writing as a fraction, as a rate here. Now, okay, so first of all, the inflow, we'd have to be told how many grams are coming in. So it's coming in at, say, half a gram per minute. Okay, and if you have a quick look at the, this, you can see here that is going to be basically, oh, sorry, not half a gram a minute, actually it should be half a gram a litre. Okay. Okay, so it's going to be what? 10 litres per minute, and it's going to be, the concentration is half a gram per litre. And if you have a quick look at that, you can see, okay, what is that? Well, coming in would be a half times 10. The litres would cancel. We are getting about, what, 5 grams per minute coming in. Okay. Now, obviously, we stir this thing continually, so the concentration inside the vat is constant. Okay, and, well, it's changing, but it's actually uniform. And so the idea is that we're coming out at 10 litres a minute, and we know that basically the concentration, initially, let's have a look at the initial concentration is. Okay, so it's 200 litres, 50 grams, so it would be what? 50 over 200. Okay, that's grams per litre, which would be, say, about a quarter of a gram per litre. So this is the initial concentration, and you can see that what's happening is that we're getting a half a gram a litre coming in. So the concentration is actually, well, it's more concentrated coming in. So eventually our, if you like, our diluted solution will increase in concentration. Well, if you like, the amount of salt in the brine solution will increase. Now, a couple of things. we need to set up an equation with this, and we're going to sort of look at our outflow rate, which you can see is 10 litres a minute, and how many grams will be coming out. Well, what would the concentration after, well, we don't know, there's 200 litres, and we just assume after some particular time the concentration is Q, like a Q grams actually per litre. So there's 200 litres. You can see here that we're going to have something like Q on our, say Q on 20 will be our, if you like, change or decay rate, if you like. So we end up getting this is a bit hard to write here, but let's write that as, say, Q on, say, 20. Okay, or a 20th of Q is coming out. Okay, now how do we set this up? Well, let's actually have, there are a couple of ways. I originally started always doing these like this. Okay, so I always originally started to do them like this, and let's actually have a quick look. What is the inflow rate? Well, it's 5 grams. You can see here, that's 5 grams are coming in. What is our outflow rate? Well, actually the outflow rate, as you can see there, was Q on 20. So we just did Q on 20 here, and dq dt. And you can, from here, you can actually set it up. So you can go, let's write that, that's what, 100 minus Q on 20, dq dt. Okay, and you turn it upside down and integrate, so you get dt dq, okay, would equal so 20 on 100 minus q. You'd integrate with respect to q, and you'd end up getting that what t is equal to. Now you've got to be careful here when you integrate with respect to q. You're going to get minus 20 ln of 100 minus q plus some constant integration. Let's just call it c. Okay, so how do we solve this? Well, we're going to have to, first of all, let's go up the top and say, okay, therefore, what's that? T minus c is equal to minus 20 ln of 100 minus q. Then we raise everything to the power e. Well, we can divide by, let's divide by minus 20 first. So it's minus, well, let's put a t minus c on minus 20, I suppose, and we can fix this up in a minute. Equals ln 100 minus q. Okay. Then what do we do? Well, we keep working on this. Let's keep working on this. Okay. So, okay, so what do we do now? Well, we raise everything to the power e. So e, now I'll just break this up to minus t on 20. Then we're going to get to what? Plus c on 20, if you like. Equals e to the ln 100 minus q. Obviously, which is going to drop us out at 100 minus q. Okay, this is going to give us what, e to the minus t on, say, 20 plus c on 20. And normally we'd say, okay, t is equal to 0. Okay, let's have a look. Say t is equal to 0. Okay, how much? Our quantity is actually, what, 50 grams of salt initially. Okay, so we then have what, e to the what, c on 20 is equal to 50. Okay, and then we rewrite this equation eventually as what? So we have 50 lots of e to the minus t on 20 is equal to 100 minus q, and we normally write q at the front. Therefore, q is equal to 100 minus 50 e to the 1/20th of t, or minus 1/20th of t. Okay, you can see here minus t on 20. Okay, now you can see as t goes to infinity, the q goes to 100. That means, what does that mean? Well, if you have a quick look at this, okay, half a gram a litre is coming in. Okay, now the initial concentration is only 1/4 of a gram over here, you can see. So eventually it'll build up to half a gram a litre. So if there's half a gram a litre and there's 200 litres, we expect there would be, what, 100 grams of salt eventually, okay, as t goes to infinity. So you can see here, this value here, okay, is in fact what we eventually get to. Okay. Now, so we can now solve this, and we can say, okay, after 10 minutes, how much salt's present in the solution, or we can do other sorts of variations on that. Okay. So, but let's actually have a quick look at the other side of it, from, if you like, the steady state side. Okay. Okay, looking at steady state and transitional state solution, I think it was Q is equal to what? R, okay, minus A e to the minus kt. And if you actually look at the steady state of this, okay, what is R, the constant? Well, R is what it's going to approach, and we worked that out. It should be about 100 grams of salt it will approach. Now, what was A? You might remember A was what? The difference between Q and R initially, and you can see here that's 50. Okay, and E, now what was K? Well, K is actually the decay constant, so in fact you can see here, that is, if you look at the outflow, there's a 20th of Q is decaying over time, so I always just think that that's really right, like minus T on 20, okay, a 20th of the amount is actually decaying. So we can actually look at this in terms of the steady state idea, and that is, you can see here that if you look at the graph, okay, initially there's 50, so down here it starts, say, at 50, okay, it's approaching the steady state at 100 over time. This is, okay, T here, this is Q up here, and you can see here it's coming up, okay, approaching the steady state. And the transitional state, which is this bit here, is basically, that's a transitional state, okay, and that's basically, if you like, coming up to 100 from below. If you like, it's actually getting smaller and smaller as t goes on. Okay, well, thank you for watching.